You know, when you think about modern artificial intelligence, it's easy to imagine it as something that knows everything with absolute certainty. But the truth is actually the opposite. Real AI is all about navigating a world full of uncertainty by making incredibly smart, calculated guesses. So, let's dive into how it does that.
I mean, think about it for a second. How does an AI tell you if you're going to need an umbrella tomorrow? It can't exactly look into a crystal ball, right? It has to work with information that's incomplete, messy, and constantly changing.
And here is the secret sauce. It doesn't know for sure. It can't. Instead, it predicts. And the language it uses to do this is probability. It takes everything it's learned from the past and stores that knowledge not as concrete facts, but as probabilities, the chances of different things happening.
So for instance, an AI agent might crunch, say, the last 50 years of weather data for the month of March. And if it finds that 45 of those 50 Marches were sunny, well, it stores that. It concludes there's a 45 out of 50 shot or a 90% probability that March is going to be sunny. That number, that probability, becomes its core belief about the world.
So here's our game plan. We're going to build the basic probability toolkit that lets an AI think this way. We'll start with why it even needs probability, get into its essential tools, learn how to read its brain from a table, add some context with conditions, and then, the really cool part, learn how it proves if two things are connected at all.
Okay, let's start with the first two tools in our AI's toolkit, joint and marginal probability. You've got to understand these two. They are the absolute cornerstones for figuring out how different events relate to each other. Before we even touch a single number, I want you to get a picture in your head. Imagine two different events, we'll call them A and B, as two big circles, kind of like a Venn diagram. Now sometimes these things happen at the same time, right? So the circles overlap. That little slice in the middle where they overlap, that is the joint probability. It's the chance of both things happening together. So, to put it formally, joint probability, which we write as P of A and B, is just the probability that both A and B happen at the very same time. Think, what's the probability that it's cloudy outside and it starts to rain? That's a joint probability.
Marginal probability, on the other hand, is a lot simpler. It's just the probability of one single thing happening, P of A, and we don't care about anything else. So what's the probability of rain tomorrow? Period. We're not asking about clouds or wind or temperature, just the rain. That's a marginal probability.
Okay, theory is great and all, but let's see how this stuff actually works in the real world. We're going to look at how an AI stores all this knowledge in what's called a joint probability distribution table.
So let's imagine we've done a survey. We went out and asked a bunch of people about their favorite TV show. Maybe it was Game of Thrones, The Big Bang Theory, or something else. And while we were at it, we also jotted down their gender. This is the kind of raw data our AI is going to learn from.
And here it is. This table is basically the AI's brain on this specific topic. Every single cell on the inside represents a joint probability. See that 0.16? That means there's a 16% chance that a person we pick at random is both a male and a fan of Game of Thrones. And those totals on the sides, in the margins? Well, those are marginal probabilities. We'll get to those in just a sec. All right, pop quiz. This is a classic exam-style question. Looking at this table, how do we figure out the probability that any random person, we don't care about their gender, prefers the Big Bang Theory? What we're asking for here is a marginal probability.
So the key here is that the question doesn't care about gender, only the show. So first thing we do is find the TBBT row. And here's a little tip to avoid silly mistakes. Seriously, use your finger to trace the row across. It stops your eyes from jumping to the wrong line. Okay, so the total probability of watching TBBT is just the sum of all the ways it can happen. You could be a male who watches it, or you could be a female who watches it. So we just add those two joint probabilities together. 0.20 plus 0.05.
And that gives us 0.25, or 25%. And hey, look at that. It's the exact same number that's already sitting there in the total column for that row. That's why they're called marginal probabilities, because they literally live in the margins of the table.
So we're building up our toolkit, but what happens when our AI gets a new piece of information? It needs a way to update what it believes. And that's where our next tool comes in. And trust me, it's a really powerful one. Conditional probability. Conditional probability is all about asking a what-if question. We write it as P of A, a vertical bar, then B. And we read it as the probability of A
given B. This means we're working under the assumption that we already know that event B has happened. So given this new fact, what are the odds of A happening now? Think of it like this. What's the probability of rain given that we look outside and see the sky is already full of dark clouds? That new info definitely changes the odds. And here's the formula that makes the magic happen. I know it might look a little intense at first, but the idea behind it is actually really intuitive. All we're doing is narrowing down our world. The bottom part, P of B, basically shrinks our universe to only include the outcomes where our condition B is true. Then, the top part, the joint probability, looks at how often our event A also happens inside that new, smaller world. It's really just the overlap, but rescaled to our new reality. Okay, this all leads us to the biggest question in data science and AI. Are two things related, or are they totally separate? Are they independent? If an AI can figure this out, it can understand the world so much better. And the cool part is, we can prove it with math. So let's use our TV data to ask a really specific question. Does knowing a person's gender give you any clue about whether they watch Game of Thrones? Or, to put it in probability terms, are the events male and watches GOT independent? Here it is. This is the mathematical test for independence. Two events are independent if and only if the probability of them happening together is exactly equal to the probability of the first one times the probability of the second one. If this equation works out, they're independent. If it doesn't, they're dependent. Simple as that. Okay, let's plug in the numbers and see what happens. Now, here's a pro tip. To avoid messing this up, always be super clear where you're grabbing your numbers from. The left side of the equation needs the joint probability. That's always one of the inner cells, at the intersection of the row and column. For us, that's 0.16. Easy. The right side needs the marginal probabilities. Those are always in the total row and column. So we grab 0.46 for male and 0.40 for GOT. We multiply those, and we get 0.184. And there's our verdict. 0.16 does not equal 0.184. The equation is false. So what does this mean? The bottom line is, these events are not independent. Knowing that a viewer is male absolutely changes the probability that they watch Game of Thrones. We've just mathematically proven that there's a relationship between these two things in our data. Phew, okay. So we've just put together a really powerful set of tools that lets an AI make sense of a messy world and find the hidden connections in data. Let's do a quick recap. So, first off, probability is the language AI uses to deal with uncertainty. Simple. We learned that joint probability is all about and. It's the intersection, the inner cells of our table. Marginal probability is just about one thing at a time, the totals in the margins. Conditional probability lets the AI update its beliefs by asking, what if? And finally, that independence test. That's our ultimate tool for proving if two things are actually related. We have covered a ton of ground, but this is really just the beginning. It leads to an even more powerful idea called conditional independence. That's when two things might look related, but the moment you learn about a third thing, they suddenly become independent. So the question is, how could an AI use that idea to filter out all the noise, simplify really complex problems, and make even faster, smarter predictions? Well, that's a great question for next time.